Welcome to our video on the conditions for deadlock. Meet the members that produced this video: Aniq, Ameera, Haikal, and Ammar. In this video, we will explore the concept of deadlock, the conditions that lead to its occurrence, and provide examples to help you understand it better. So, let's dive in. In a multitasking operating system, various processes are running concurrently, each vying for shared resources such as CPU time, memory, or devices. Deadlock occurs when two or more processes are unable to proceed because each is waiting for a resource that the other process holds.
The first condition is mutual exclusion. It states that a resource can only be used by one process at a time. For example, when a process acquires exclusive access to a printer, no other process can print until it releases the printer. This exclusivity can create a potential for deadlock if multiple processes require the same resource simultaneously. The second condition is hold and wait. It means that a process holding at least one resource is waiting to acquire additional resources held by the other processes. Consider a scenario where process A is holding resource 1 and waiting for resource 2, while process B is holding resource 2 and waiting for resource 1. This circular dependency can lead to a deadlock situation. The third condition is no preemption. It states that the resources cannot be forcibly taken away from a process. Once a process acquires a resource, it will keep it until it releases it voluntarily. This condition increases the likelihood of deadlock because a process holding a resource indefinitely may prevent other processes from progressing. The fourth condition is circular wait. It means that there must exist a set of processes in which each process is waiting for a resource held by another process in the set. This circular chain of waiting creates a deadlock scenario, as no process in the set can proceed until it acquires the resource held by another process.
Deadlock occurs when all four conditions are simultaneously present in a system. If any of these conditions is absent, deadlock cannot occur. Understanding these conditions is crucial for detecting and preventing deadlocks in a computer system. Now, let's see a couple of examples to illustrate how these conditions lead to deadlock.
Let's consider two processes, P1 and P2, and two resources, R1 and R2. Processes P1 holds resource R1 and requests resource R2, while process P2 holds resource R2 and requests resource R1. Both processes are waiting for a resource held by the other, resulting in a circular wait which satisfies the deadlock condition. Let's consider a more complex scenario with multiple processes and resources. In this case, process P1 holds resource R1 and requests resource R2. Process P2 holds resource R2 and requests resource R3. Process P3 holds resource R3 and requests resource R1. And process P4 holds resource R4 and requests resource R3. This circular dependency among the processes and resources creates a deadlock situation.
To prevent and resolve deadlocks, various techniques can be employed, such as resource allocation graphs, Banker's algorithm, or using timeouts and resource preemption. And that concludes our video on the conditions for deadlock. We hope you now have a better understanding of the conditions that contribute to deadlock and how they manifest in real-world examples. Remember, proactive detection and prevention of deadlock are vital for ensuring the smooth operation of computer systems. Thank you for watching.